All right, good morning, everyone. So, welcome to the home stretch of the term. We have only a couple classes left. So what else do we have to do this week? This week is the last of the Prairie Learn homework. That's due on Thursday, the last day of classes. If you're completing hands-on bonus projects, the deadline to send me your YouTube link is today. So we received our first submissions over the weekend, and I posted those links on Canvas. So if you want to see what some of your classmates have been working on, those links are going to be available, and I'll keep adding to them as I receive new submissions. There's also on Canvas a link to an end-of-term survey that will be open until Wednesday. So please complete that for your 0.5 grades towards your final mark. And then last thing, today is the eclipse. Where we are, we don't see a total eclipse. We'll see just a partial eclipse of the sun. And the peak of the eclipse for us is, I think, around 11:30 a.m. this morning. The forecast is clouds and rain, so we'll see how all that turns out. But it's worth a look if you're interested. Okay, so what we were working on last time was this kind of the last topic for Phys 121, and it was motional EMF, or really kind of on a bigger picture. The last topic is creating electrical energy from mechanical energy. So that's what we're going to do. In this case, the mechanical energy was the motion of this conducting bar that's being slid across a circuit made of conducting tracks with a resistor on the left-hand side. And then we apply a magnetic field that's perpendicular to this apparatus. And so the idea was, if we pull the bar to the right at some constant velocity, then we have free charges inside the conductor moving through a magnetic field. They experience a force. What we said is positive charge would tend to be deflected towards the top of the bar and negative charge towards the bottom of the bar. And when you get that motion of charge, that establishes a current. If we have a complete circuit, that charge can move around that circuit. And so positive charge flowing upwards corresponds to a current going upwards through the bar and then around the circuit in a counterclockwise sense. So what we were able to do is we were able to calculate last time the induced EMF, or the voltage difference induced by dragging this bar through the magnetic field. The current that we would get if we set up this circuit, which is just that voltage divided by the resistance of the circuit, as well as the power that would be dissipated by the resistor. It was just I squared R. So if we take I squared multiplied by R, that's the dissipated power. The last thing we did is we said, oh, okay, well, let's hold on a second. If we were to have a current going upwards through this bar, and there's the magnetic field present, then we know that the force on the magnetic field the force on the current due to the magnetic field would be I times L cross B. Sorry, maybe I should use the same notation. We have FE for the magnetic force on our current. The vector L is just the length of the bar, or the distance between the two parallel tracks of our circuit. And direction is in the direction of the current, so it's upwards. And then when you cross with the magnetic field, I curl my fingers into the screen in the direction of the magnetic field, and it tells me that the force is to the left. Or in other words, the force is in the opposite direction of the velocity that we're pulling this thing with, to the right. So if I want to pull this thing to the right with a constant speed, I have to all the time overcome this magnetic force that's acting on this current. So to maintain a constant speed of the bar, we must pull with a force, let's call it F pull, that balances the magnetic force FB acting on the current in the bar. Okay, so on our picture then, what we have to do is we have to provide, here, maybe I should put my L back here. We have to provide an F pull to balance the magnetic force. Now, if we're pulling on this bar with some force F pull, as it's being displaced to the right, force times displacement is work. So we have to put energy into the system to do this. The work we do to pull the bar is, so the work is F pull times whatever the displacement is. And so this is our displacement. Now, if we want to pull this constantly, so it's always sliding, what we probably are interested in is the rates that we have to put energy into the system, or the amount of power that we have to provide in order to move that bar at a constant speed. So the power input into the system is power is going to be the amount of work we do per unit time. And so that's just going to be whatever the force is that we pull with times delta x, but then I'm going to divide by delta t. And so if I take the displacement of the bar, divide by how long it took to move that distance, that tells me the speed of the bar. And so this is just exactly equal to V. And so the power that we put in is F pull times the speed. Now I should be careful. Let's call this the power in, and this is going to be the dissipated power by our resistor. And so I'm going to compare in the end how much power we put in to how much power gets dissipated by the resistor. So there it is. Now we require sorry, this should be an F. This is a force. The force times the velocity or the speed gives us the power. So we require the F pull to be equal in magnitude to this magnetic force, which was I times L times B. But we know I from equation 3, and so it's VB times L divided by R. So we'll sub 3 for I. And so then our F pull is going to be VBL divided by R, right? It's the EMF, or the voltage difference, divided by the resistance is the current. And then we have L times B. So therefore, power in is going to be equal to F pull, VBL divided by R times LB. So this is all of the pulling force And then we have to multiply by the speed. And so now when you look at this, we have in the numerator, VBL times VBL. So it's VBL squared in the numerator, and then it's all divided by the resistance R, VBL squared divided by R. And so this is the power put into the system, VBL squared over R. And if you go and look back at equation 4, which is the power dissipated by our resistor, VBL squared divided by R. So this is kind of a nice confirmation of conservation of energy. The amount of energy that we put into our system is equal to the amount of energy that's dissipated by the resistor. Now, in practice, there might be other things that would be happening if we're really pulling this bar along a track. There will be some kinetic friction. And so some of the power that we put into the system will be lost to heat that gets generated in that friction. And so it would, in practice, would be more complicated, but in an idealized situation, we have this confirmation of conservation of energy. So notice that P in is equal to P, which is the power dissipated by the resistor. Okay, and so this is conservation of energy. Oh, okay. All right, there we are. Back in business. Okay, so what I want to do is, everything we've done is completely true. What I want to do is I want to generalize this and see if we can come up with a more kind of first principle way of calculating these induced EMFs and the currents and so on. And so I want to just go back and just look at this picture for a second. And we've got this bar sliding on a track through a magnetic field, and we generated a current. And so one thing that I want to notice is that for this problem, the magnetic field is completely constant. So the current is not generated because we're changing the strength of the magnetic field or something. What is changing is the area of our circuit loop. And so if we said that our height or the distance between the parallel tracks is L, we could also label, for example, the horizontal dimension of our circuit. And at the instant that I've drawn it, it maybe has this length X. But at some time later, if I'm pulling this to the right, X is going to increase. And so we could say that the area of our circuit is increasing or changing. And that's going to turn out to be important. So what we're going to do is we're going to see if we can get the motional EMF result. And let me remind you, it was the induced EMF was VBL, and we're going to try to get this in another way. All right, so I'll draw the picture again, the picture that we've always been using. Here we have our uniform and constant magnetic field that's going into the screen. And then we'll draw our track with our resistor. Actually, let me first put in the bar. So here's our bar, and it's sliding along a track that has some resistor R, and then returns along this direction. So there we go. Here's R. This is the length L, and I'm going to make a coordinate system. I'll make an x-axis. And so at this instant, we're at some position x along this axis. Okay, and we're moving this thing with some velocity v to the right. So that's just the normal setup that we've been dealing with for the past, 3/4 of a class or something like that. So what we're going to do is we're actually going to calculate the magnetic flux. So we did a bunch of flux calculations for electric fields when we were talking in particular about Gauss's law. And so I want to do something similar for magnetic fields. But in this case, the geometry is really simple. Remember, the way we calculated electric flux was this integral of E dot dA. So there was a dot product, and so it mattered what was the relative direction of the electric field and some surface that we're dealing with. We could, in principle, have an electric field that's varying over the different parts of the surface, and so that complicates the calculation. All of this in this geometry is much more straightforward because we have the magnetic field exactly perpendicular to our area. And so remember, the way we got the area direction was to put a normal vector, a vector perpendicular to the area. And so in that case, if we have a vector dA perpendicular to the area and the magnetic field's also perpendicular to the area, the angle between those two is 0. So when we do the dot product, we'll get cosine 0 is 1. So the dot product goes away. The other thing we have is a constant magnetic field. And so I don't have to do the integral because the magnetic field is the same everywhere. So what we're going to do is we're going to calculate the magnetic flux through the circuit loop of area. So the area is going to be L times X. Okay. So in general, the magnetic flux is given by so it's the exact same expression that we had for electric fields, except instead of an electric field, we'll have a magnetic field. So it's B dot dA. So as I said, in this case, for a constant magnetic field that's perpendicular to our area, this simplifies quite a bit. For a constant magnetic field with B perpendicular to our area, the magnetic flux is just going to be equal to B times A, which is BL times X. And you can already see that parts of the result that we're trying to get are sort of emerging. We want to show that the induced EMF is V times B times L. So right now we have V times L, but instead of a V, we have an X. So how do you go from a position X to a velocity V? What's the relationship between position and velocity? Yeah, that's exactly right. So let's consider the derivative with respect to time of the magnetic flux. So it's going to be d by dt of BL times X. But in this case, we've already said that the magnetic field's constant L, the distance between the top and bottom tracks, is going to be a constant. And so they don't have any effect on the derivative at all. So we say since E and L are constant in the current problem, or the problem that we're working on, we get that the derivative of the magnetic flux with respect to time is equal to BL dx dt. And dx dt is just the speed. And so therefore, this is equal to VBL, which is the same result that we got before. This is equal to the induced EMF. And it's in general true that if I want to have an induced EMF or an induced voltage difference, what I need to do is I need to change the magnetic flux in some way. And it turns out that there's multiple ways of changing the magnetic flux, and we're going to talk about all those various ways. We've seen a few demonstrations of these already, and I'll try to show you one more. Okay, so it is generally true that the induced EMF in a circuit is equal to the time derivative of the magnetic flux. And so we can summarize that by saying the induced EMF is given by this derivative. I'm going to put an absolute value sign around there. Okay, so I'm not worried about the sign of this voltage difference right now. I'm just worried about the size, its magnitude. We'll discuss the sign probably a little later today. And this is known as Faraday's law. So this is one of the last big results that we'll develop in Physics 121. Okay, so what I want to think about is all of the different ways that we can change the magnetic flux through some loop. So we can change the magnetic flux, which I'll label phi b, through a loop. And I'm going to claim 3 different ways. Okay, so first let me just write down the expression for the magnetic flux. It's B dot dA, like so. I think I've been using a small a. And so if we wanted to expand out the dot product, we could write this as B cos theta times dA. Okay, so what's one way that we could change the flux? If you look at these expressions here, and I want to change phi in some way, just name one way that I could do that. I have a magnetic field, I have some kind of area, there's a theta. What could I do to change the flux through some loop? Change theta, okay, there we go. So we could say one way to do it is to change the angle between the magnetic field B, or let's just say between the magnetic field B and the area dA. Okay, so I could draw a picture of that. Let's imagine that we had some magnetic field that was pointing off to the right here, and then I have some surface. So let's say I have some surface. This is like a side view. Side view, and this red thing is the edge of a loop. So that's like a coil of wire or something like that. We're just looking from the side. Okay, so then the dA is going to be perpendicular to this area, and the angle theta is the angle between that area vector and the magnetic field. And so right now, I'm at some theta that's maybe, I don't know, just for simplicity, let's call that 45 degrees. So I'm at some intermediate angle where cosine of 45 is like 1 over root 2. So 0.707 or something like that. But then if I change the angle so that the theta becomes 0, then the cosine of 0 is going to become 1. And so I've changed my cosine factor from 0.707 to 1, and that's definitely changed the flux through this little loop. I could also change it the other way. I could change it so that the angle goes to 90 degrees. In that case, the cosine of 90 will be 0, and there'll be no magnetic fields passing through the loop because I'll have the plane of my loop parallel to the magnetic field. So if we rotates the loop so that theta changes, then we create a change in the magnetic flux through the loop. And we expect an induced EMF. Okay, so that's one way we can do this. And I've got a bit of a little demo here. So let's see if I can make this work. So I'm going to share the computer screen. Okay, so there we go. And sorry. Why can't I? Okay, let's start the video. Okay, and let's see if I can expand this. Okay. Okay. Here we go. I'll get there eventually. Oh. Okay, that's pretty good. So let's see. I just want to make sure everyone can see this. Okay, good. So what we're going to do is I've got here a current meter connected to a little coil that I can rotate. And so here, I can rotate this coil here. It's just a coil of wire that's wrapped around many, many, many times. And then this is a magnet. And so here's some iron post. The magnet is going to be used just to magnetize these iron posts so that if the blue one is the north pole of the magnet, then the red one's the south pole. I would have magnetic field lines pointing from the blue to the red. And if I put my coil like this, I get the most possible magnetic field lines passing through these loops. And all I'm going to do is I'm going to spin this thing, and we'll just watch the needle on the little current meter. And so let's see if this works. Okay, so when I spin it in one direction, I pin the needle. Sorry, let's see. There we go. So I pin the needle to the negative side of the current meter. And all I'm going to do is I'm going to spin this in the other direction. And I pin the needle to the positive side of the current meter. And so I can create these induced EMFs, which drive currents in this loop, and we can measure that current. I can spin it in one direction, I'll get a current flow in one direction. I spin it in the other direction, I get a current to flow in the other direction. Okay, good. Just before I turn off this video, you could also do the opposite. We're talking about converting mechanical motion into electrical energy. We could instead provide a current to the coil and have that current flowing through a magnetic field. The magnetic field will exert forces on that current and it'll cause the thing to spin. So that would be like an electric motor. So if you use like a battery powered drill or whatever, something like that, what it has inside of it is these coils of wire and some magnets, and you put current through the coil with the battery, and then that starts spinning inside the magnetic field. The demo that we did, inducing currents with the motion of the coil, is the basis of almost all power generation that we use to power our homes and cities and so on. So in BC, we use a lot of hydro dams. What the hydro dam does is you take water that's at a high level, so it has high gravitational potential energy, and you let it flow down a hill, a slope of some kind. And as it flows down the slope, we convert the gravitational potential energy into kinetic energy of the rushing water. That rushing water goes through a turbine. And as it goes through the turbine, it spins a coil of wire inside large permanent magnets, and we get the induced EMFs, voltages and currents that are then distributed to households and cities and office buildings and whatever we have. Even if you're burning coal, what you're doing is you're burning coal to generate steam. And then that steam is rushed through, again, some turbines. And it spins the turbines, which spins a coil of wire through a magnetic field. If you're working at a nuclear power plant, you're using nuclear energy to heat water to generate steam. That turns the turbine that spins coils through a magnetic field. So however you're doing it, you're always using the same Faraday's effect to generate this power. And it is the idea that we are changing the magnetic flux through our coil that's allowing us to do this. Okay, good. So what I'm going to try to do is go back to the tablet here. Okay, and what I think I need to do is to get rid of this. Oh. Okay, what am I doing here? How do I, here we go. Oh no. Okay, I don't know. How do I get into full screen? Here we go. Okay, I think I'm gonna just go like this for now. All right, so that's changing the angle. What's another way we could change the flux? The flux involves magnetic field, the angle we've already dealt with, and like an area. What's another way we could change the magnetic field? Or sorry, change the flux. Yes, change the strength of the magnetic field. Okay, so one way we could imagine doing that is I could take a loop of wire, and so I make some area A through this loop of wire, and then I bring near this a bar magnet. And so this bar magnet, if this is the North Pole, is going to make a magnetic field that points out of the North Pole, and some of those field lines will pass through our loop. So if I keep the magnet completely steady and I keep my loop steady so they're not moving relative to one another, then the magnetic field and the magnetic flux through that loop is constant and nothing will happen. But if I was to suddenly pull the bar magnet away, I would decrease the magnetic flux through the loop. We would get an induced EMF and an induced current. I could also take the magnet and I could push it further closer to this loop, and I'll increase the magnetic flux through that loop, and I'll again get an induced EMF. It'll just be in the opposite direction. So we saw a demonstration of this, I don't know, like a couple weeks ago where I had, remember the coil with some two LEDs, a green one and a red one. If current flowed in the coil in one direction, the green LED came on. If it flowed in the opposite direction, it was the red one. And then we had a strong magnet and I moved it in and out and we could see the LED flash on and off. You also did this in lab number 8, where we slid a magnet down a copper track. And so as the magnet slides down to some new region, the magnetic field strength increases in that region and we get these induced currents. So if we move the bar magnet towards or away from the loop, we change the magnetic flux and get induced EMF and a current. Okay, the third way that we can change the magnetic flux is just to change the area of the loop. And an example of that is the motional EMF that we've been talking about for the past couple of classes. And we saw like a video demonstration of that where someone was sliding a metal bar along these metal tracks through a magnetic field. And we saw the change in the current, just like we saw today with this spinning coil. So the third way we can change the magnetic flux is to change the area of the loop. So if the magnetic flux is equal to BA cos theta, and we change A, then the resulting change in magnetic flux creates an induced EMF and current. the motional EMF is an example of induced EMF due to a changing loop area. Okay, good. So the last thing we have to do for our discussion of Faraday's law is to try to understand what are going to be the directions of the voltage difference that's created, the induced EMF, and the resulting current that flows. Okay, so let's consider the direction of induced EMF and current. We'll go back to, because we've invested a bit of time into understanding them, we're going to use our motional EMF as an example to work out what's going to happen. So there's two cases. The first case is the one that we've been talking about already. We're going to pull this bar in our motional EMF example to the right so that the area of our loop increases. So this first case is we increase the flux by B through a loop. Okay, so we have to draw the usual picture that we always draw. So we'll have our magnetic field, we'll have our bar being pulled to the right, and we'll have our conducting track. So there's our bar, here's our velocity for our bar, our conducting track is doing this, like so. Okay, so let's just remember what we were talking about before. So the force on the charges inside the bar are QV cross B. So we go V to the right, cross B into the page. The force on a positive charge would be upwards. And so that means we're going to have a current that flows in this direction. So this is I induced. So this is the induced current. Here's the magnetic field. And in this induced current, we'll go around like we drew before in the counterclockwise sense. So by the right-hand rule, the induced current in this case is counterclockwise. Okay, so that must mean there's an electric field that points, let's see, the electric field must point downwards, the electric field must point in the other direction. I see, yes, we're going to have positive charges moving upwards like so, and we'll have negative charges, electrons, moving down towards the bottom. So this is our high potential side, and this is our low potential side. High potential is at the collection of positive charges at the top, and low potential is at the bottom, where the negative charges collect. Okay, the induced current, creates its own induced magnetic field. I'll call this magnetic field B induced. Now, by the right-hand rule, if I curl my fingers in the direction of the current for counterclockwise sense, my thumb gives the direction of the induced magnetic field. It's coming out of the screen. It's in the opposite direction of the field that was established originally, the blue field. So this is B induced, and it's coming out of the screen. So the main takeaway from this picture is that when we increase the magnetic flux through the loop, we're pulling the bar to the right, we're increasing the area of the loop, and so more and more of the blue magnetic field lines pass through. So that's the increasing flux. The induced magnetic field acts in the opposite direction of the original field, the blue one. So when we increase the magnetic flux through a loop, the induced magnetic field B induced opposes this change in flux by having a direction that is opposite to the direction of the original field. Okay. What I want to do is I want to do case number 2, which you could probably guess what the result is going to be. So we have 4 minutes, so we could do case number 2. So case number 2 is we're going to decrease the magnetic flux through our loop. All right, so the geometry is going to be very similar. We'll have the same blue magnetic field going into the screen. We'll have our same bar and our same track. All we're going to do is we're going to pull the bar in the opposite direction. So instead of sliding it to the right, we'll slide it to the left. And sliding it to the left will make the area of our loop shrink, so that we'll have less and less magnetic field lines passing through our loop. Okay, and so we're going to pull this to the left this time. All right, so if I do V cross B now, V is now to the left. So I put my right arm to left for the velocity cross B. B is into the screen. Now my thumb points down. So we would have positive charges deflected towards the bottom of our rod. So we have positive charges piling up over here. This is where we would have our high potential. And we'd have negative charges over here. This would be our low potential. Current is in the direction of positive charge flow. So we would have our induced current would now be down. And because it's part of a circuit, those charges could flow around the loop in the clockwise direction. And by the right-hand rule, if my current is clockwise, I curl my fingers so that they're rotating in the clockwise sense, and my thumb points into the screen, which is the direction of the induced magnetic field. And so I was about to do the wrong direction. This is B induced. And so the summary is that in this case, the shrinking area causes a change in flux that induces a clockwise current. The clockwise current establishes a induced magnetic field. Be induced that is into the screen, or it's the same direction as the original blue magnetic fields. So we're out of time, but let me just summarize both of these observations in one statement, and then we'll recap at the start of Wednesday's class. If I decrease the magnetic flux through this loop, the induced magnetic field acts to try to oppose that change. So it wants to maintain the original magnetic flux that it had. So if we're decreasing the flux through this loop, the induced magnetic field is in a direction to try to bring that magnetic flux back to where it was. It's in the same direction as the original field. In the first case, when we increase the magnetic flux, the induced field opposes that change, and so it contributes flux that's in the opposite direction, and so the induced magnetic field is in the opposite direction as the original. Okay, so we'll recap that next time. That's called Lenz's law, so we'll write down a definition of Lenz's law, and then all we're going to do last class is just do examples of working with Faraday's law. Okay, good. Thanks very much, and we'll see you next time. Yeah.
This is perfect.
So if I wrote that down, then that's not quite right here. Let me just